Welcome to ECE3300 at the University of Utah. In lecture number 17, we're going to talk about Gauss's law for the electric field. Gauss's law gives us a way to calculate the electric field or the electric flux density from a charge distribution. We've learned of another way to do that. That is Coulomb's law. Coulomb's law can be used for any charge distribution. Gauss's law can only be used if that charge distribution is symmetric. The things we'll be covering today are the point form of Gauss's law. Then we'll integrate that over a volume and find the total charge enclosed. We'll apply the divergence theorem to convert the volume integral to a closed surface integral, and that will give us the integral form of Gauss's law, which is the form we most often use. So let's begin with the point form of Gauss's law. This gradient right here is given as d by dx in the x direction plus d by dy in the y direction plus d by dz in the z direction. What this represents is a change in the x direction, or a change in space. When we dot that with the electric flux, which we can write as having three components, a dx component, a dy component, and a dz component, what we get is a change in the x direction of dx plus a change in the y direction of dy plus a change in the z direction of dz is equal to the volume charge density. Volume charge density is given in coulombs per meter cubed. So what this means is that if we have one little coulomb in a meter squared region, it's going to create a change in the x, a change in the y, and or a change in the z direction, as we've discussed in the past. Normally the way we apply this form of Gauss's law is to be given the electric flux density and then calculate the volume charge. The other thing that we might do is know the volume charge and be able to calculate the electric flux density. Now let's see what would happen if we took the point form of Gauss's law and we integrated it over a volume. So just integrate both sides by dV. We can see right here that if we take coulombs per meter cubed, the volume charge density, and we integrate that over a volume, that we will get the total charge that's enclosed by that volume. Q is given in coulombs. Rho v is given in coulombs per meter cubed. We then apply the divergence theorem. The divergence theorem is just a mathematical theorem that says the divergence of any vector integrated over a volume is equal to the closed surface integral of that vector. So we can apply that to the electric flux density as shown here. So the form that we're going to use is going to be the closed surface integral of the electric flux is equal to the total charge enclosed. This gives us the integral form of Gauss's law. Now let me show you the steps to applying the integral form of Gauss's law. First, be sure that your charge is symmetric. That is absolutely critical, or you can't apply this law. That means that if you have some kind of a surface, that d must be equal in magnitude everywhere on your Gaussian surface. For instance, let's take our little charge here and let's draw a spherical surface around it like this, of radius r. We can see or imagine that the electric flux would be equal in all places. The magnitude of the electric flux would be equal here, and here, and here, and every place else on this sphere. This is a case where our charge distribution is symmetric. If it wasn't, for instance, if we had two charges like this, we can see that the electric flux density would be stronger over here next to the second charge. In that case, we would need to use Coulomb's law instead of Gauss's law for the electric field. The next thing we do is we choose a Gaussian surface so that my field point is on it. For instance, in the case where I had my charge right here in the center, the surface that I've chosen is really good because I can find my electric flux any place out here on the outside of the surface. I'm then going to do the integral on the left-hand side. That's always the same. I'll show you what I mean in a minute. And we'll do the integral on the right-hand side to find q, and then we'll solve for d, and if we wanted to find e, we'd find it knowing that d is equal to epsilon times e.